Hello and welcome back to today's tutorial in quantum mechanics. I just want to emphasise that your first assignments have been marked. You can pick them up from the table here. You can pick them up from the table here. If you're not here, then I'll return these to the third year labs to be picked up. Assignment 2 was posted online. Assignment 2 was posted online and the due date was originally Saturday week, but I figured it's a bit harsh handing it in on a Saturday, so Monday week is now the due date. Lastly, I want to emphasise that all of the lectures and all of the tutorials are available online. And as a special bonus for watching the YouTube videos of these classes, I invite you to spot the frogs that appear spontaneously in various places, courtesy of Steve Morton. Today's tutorial, I want to be fair, which is our last tutorial. I just want to remind you that both classes on Friday will be lectures, lectures 11 and 12 respectively. In today's tutorial, I want to be fairly amorphous and see how it goes. I want to go through the 3 clouds animation question from the assignment. I want us to discuss the meaning of the spin 1 wave function in a little bit more detail. I want to put these two things together to discuss a very contemporary question in modern physics, the so-called spinor Bose-Einstein condensate, one of which, by the way, exists at Monash here in Lincoln Turner's laboratory. I want us to guess the equations that describe this quantum system. I then want us to discuss a little bit about the connection between theory, modelling and experiment in modern physics. And if we have time, let's discuss further Hawking's deliberately provocative quote that equations are the boring part of physics. So let's kick on off with the 3 clouds question. So this was the series of simulations which plot a probability density, rho, as a function of position and time. But this is a 2-dimensional world where you only have x and y. And in your assignment, we had the question where we had 3 clouds and the probability density for a sequence of times was plotted. So as I go from left to right, let this describe a sequence of times. Now you've all watched the video that was online as part of the first assignment, but I just want us to go through the physical meaning. In the question, I asked you to describe 6 non-trivial, distinct physical points regarding the physics of what's going on here. So we have a parabolic trap, yeah? So this is a trap, there's a potential minimum in the centre. The trap is rotationally symmetric. This would be a V equals a positive constant times x squared plus y squared. This is a parabolic bucket. And we start off with 3 separated clouds. Now this is not, the wave function here is, as always, going to be related to the probability density in the usual way, but this thing is not going to obey the Schrodinger equation. It obeys some more exotic equation, which we'll discuss soon, and which was given in the assignment. So we began with 3 initially separated clouds. Now let me draw these clouds a little bit smaller. So these are 3 initially separated clouds. Then we wait a little while and we see this wave function evolve. Can someone describe to me how this wave function, or more precisely this probability density, evolved for a small time? If you wait a small time, what happened to these 3 clouds? They'll expand. So these 3 clouds expand, and this expansion of the 3 clouds as they grow older is an example of it's an example of the spreading of the wave packet, the idea that, the very general idea that typically localised wave packets tend to become progressively more delocalised with time. So these things expand. So if we go to some later time, these packets are going to get bigger, but they don't just get bigger, they also they interfere with each other, so they're getting bigger. They're also sliding down the hill. Notice that I'm representing the centre of mass of these three packets as sliding down, because they're going to be heading towards the centre, the potential minimum. And this motion of the centre of mass will be in accord with Ehrenfest's theorem. If you had a parabolic bucket, a paraboloid of revolution that was a bucket, and you put billiard balls here, then those billiard balls would accelerate down towards the centre. In fact, that exhibits simple harmonic motion. But you now make the point that they interfere when these clouds expand enough. Then they begin to overlap. Yep, then they begin to overlap, yep. And in these regions of overlap, we start to see Young-type fringes. So between any pair of clouds, we have two adjacent clouds interfering, and this is analogous to Young's interference experiment. And so these are sketching the Young's interference fringes from this idea of them beginning to interfere. Let me also look at this from a symmetry perspective. So I'm going to ask this question deliberately loosely. What is the symmetry of this situation here? What do I mean by symmetry? If I speak of a sphere as being a symmetric object, so I'm asking about to look at this from the perspective of symmetry. When I say that a circle is symmetric, what do I mean precisely from a mathematical perspective when I speak of a circle being symmetric? Yeah, if you rotate it, it looks exactly the same. Yep. So I would call this, if you rotate it by any angle about the centre of the circle, then this object is unchanged. I would call this, by the way, a continuous symmetry, because there's a continuum of angles, theta, about which I can rotate this disk or this circle about the origin. Now let's take a triangle. We speak of it as being symmetric in some sense. What do we mean there when we speak of a triangle as being symmetric in some sense?
It looks the same if you rotate it by specific angles.
Yep, so it looks the same if you rotate it by specific angles. So if you rotate by any integer multiple of 120 degrees, you get the same thing back again. Closely related to that is that if I were to reflect in the xy plane through any one of these three symmetry axes, I get the same thing. In both cases, we would speak of this thing as being a discrete symmetry. So we've given an example of a continuous symmetry and a discrete symmetry. Mathematician Innes wants to generalise. Can we generalise this to give a generalised definition of symmetry? What word was common to both explanations of the symmetry of the circle, of the discrete symmetry, continuous symmetry of the circle, and the discrete symmetry of the triangle? Rotation and reflection. So this object was unchanged under a certain operation, which happened to be rotation. This object was unchanged under a certain operation, which happened to be a reflection. So we speak of the symmetries of mathematical shapes as if under certain operations, in this case rotation or reflection, if under a certain operation a given geometric object is unchanged, then we would speak of that as a symmetry of the shape. Let me make this a little more abstract. Suppose I was to ask you about the symmetries of laws of physics. Now, I've flippantly before said the universe doesn't care where you stick your fingers. Newtonian mechanics works in this XYZ coordinate system. Newtonian mechanics works in this XYZ coordinate system. Now that is a trivial point, but it's also a profound one, right? Newton's equations, Einstein's equations, Maxwell's equations, Schrodinger equation, all the laws of physics don't have a preferred direction. That's an example of a symmetry, not of a shape, but of a law of physics. So here we would speak of a symmetry as the invariance of a shape under a given operation. The laws of physics have no preferred direction, and this is a symmetry, not of a shape, but of a law of physics. But coming back to this, this scenario has the symmetries of a triangle. Yep, this has the symmetries of a triangle, precisely that discrete symmetry we discussed earlier. And each of these frames has the same symmetry. So evolution in time is preserving the symmetry. The threefold symmetry would speak of this as a discrete threefold symmetry. Okay, so these things expand and they interfere. And so far we have an analogue of Young's experiment. We still have our threefold symmetry. We still have our threefold symmetry. And sorry, since the vertical axis is a symmetry axis, let me be better and represent the threefold symmetry as follows. The Young's fringes still exist, but something special happens in the centre. We see a series of dots. We see a series of dots, a lattice of dots. And this lattice of dots is a formation of a lattice of vortices and anti-vortices, whirlpools going clockwise and whirlpools going anti-clockwise. And it was an interesting discovery that these quantum mechanical whirlpools, these states of angular momentum, some clockwise, some anti-clockwise, a lattice of points with the symmetry of the triangle, could be created through interference. Now, as time passes further, we get a series of diagrams that is beyond my graphics capabilities to draw. So one thing that happens is that this threefold symmetry is lost. This system makes a transition to a turbulent regime where the behaviour is chaotic and random. Why does this symmetry disappear? Why does the threefold symmetry disappear if you wait for long enough? Let me ask a related question. What's your understanding of the butterfly effect in chaos theory? Anyone? The idea that if the butterfly, I go for it.
A small change, you know, a long way away can have a big effect a long way away.
Yeah, so a small change a long way away can have a big effect. Arbitrarily small changes can have arbitrarily large effects. And this is when you're talking about nonlinear equations. Nonlinear equations that don't obey the superposition principle. Now, what equation governs this system? It's not the Schrodinger equation, but it's a modification of the Schrodinger equation. So let me write down the Schrodinger equation, but we're in 2D, so instead of Laplacian, it'll be d squared by dx squared plus d squared by dy squared. Plus a potential, and this is actually this parabolic confining potential, acts on a wave function, which will be a function of x, y, z and t, to give IH cross d by dt. Now this potential I mentioned earlier was a parabolic confining potential, so it will be some number, I don't know, a times x squared plus y squared. So this is our time-dependent Schrodinger equation. This is linear, it obeys the superposition principle. But these objects don't obey this equation. There's an extra term in here, a plus something, and that something is a number times the magnitude squared of the wave function. And with this term here, the equation is no longer linear. If A is a solution and B is a solution, then the sum will not be a solution, because this term, magnitude of psi squared times psi, is certainly not linear in psi. So this is a nonlinear equation, and nonlinear equations can exhibit chaotic behaviour, apparent randomness. And this so-called butterfly effect is the following. If I infinitesimally change the state now, so let's take a turbulent system, the weather. I infinitesimally change the state of the weather by having a butterfly in the Amazon flap its wings instead of not flapping its wings. It's no exaggeration to say that 1 year later, the state of the weather will be completely different to what it would have been if the butterfly didn't flap its wings. That sounds outrageous, but it's an example of this idea that arbitrarily small deformations or alterations of the given state of a system, if it's nonlinear, those arbitrarily small fluctuations grow exponentially with time. They'll always have a significant effect if you wait long enough. So this is the so-called butterfly effect. Now here we have this system of this equation looks harmless enough. Start off with this, have an initial state which is very close to 3 Gaussians. We could solve the Gaussian wave packet for the linear Schrodinger equation. Let me ask the question, can you solve this thing exactly for the nonlinear Schrodinger equation, which is what this is, or more precisely, this is a nonlinear Schrodinger equation. Can you write down the answer with pen and paper mathematics? The answer is no, no one can, no one can, and the consensus is that it's impossible, right? Now, whether it's impossible or not, we can't solve these equations. It's an unfortunate fact that most equations in mathematical physics can't be solved with pen and paper. Instead, we get as much insight as we can analytically through mathematics, through theory. But eventually, pen and paper mathematics fails us and we need to go to computer modelling. Yep. And that video that you saw in this assignment question is an example of computer modelling, where this system is solved numerically. Now, the initial system has this threefold symmetry, but there's noise present. There's no butterflies flapping, right? But you have a Cartesian grid underneath, which has a symmetry that's incompatible with the threefold symmetry. Secondly, you have numerical precision. If you're working to double precision, how many digits of accuracy is that? I can't remember. 18? Let's pick 18 as a number. If you're working to 18-digit precision, you've still got that 19th digit that's going to be a bit random, right? You say 1 part in 10 to the 20, who gives a stuff? But this is the nonlinear system. That noise due to the 1 part in 10 to the 20, and think how small 1 part in 10 to the 20 truly is, right? My height is 10 to the 10 times that of an atom. So 10 to the 20 is the ratio of my height to the height of an atom squared. So it's a vast number. It's almost cosmological in size. Yet, you run the simulation for a few seconds. And that video, by the way, was real time rates. This is how it would actually evolve in time, over the order of a minute in a lab, and they can build these things. Those tiny fluctuations due to numerical noise eventually rise and completely alter the solution. And one of the consequences of that is that solution becomes chaotic. It becomes chaotic, and this symmetry is broken. If you were to do the experiment physically, you would also get this breaking of symmetry, except now it's due to quantum fluctuations, or the fact that no experiment will be set up with perfect symmetry. So the same nonlinearity, which is the essence of why we can't predict the weather in a year, is also the essence of why we can't precisely predict this quantum state. But from a statistical perspective, the evolution that you saw has all the statistical characteristics of how it should evolve. Other physical features include, this is a parabolic bucket, so-called breathing, where the probability density breathes in and breathes out, breathes in and breathes out. There's also random noise, random sound, where you see sort of little random ripples covering the whole system. So these are some examples of the physics which underlay this system here. Now I want to go back to this equation here, this nonlinear Schrodinger equation, also called the Gross-Piotrowski equation. So this thing is used to, whether there's 1 or 2 I's or a Y, depends on which book you read. I want to look at this equation here. When I circle this, if G equals 0, we've got the Schrodinger equation. where you have a potential like this. Yep. So there's, let's assume time-independent potential. But when you switch G on from a non-zero value, the potential is replaced with a new object, which is the following. Now just for the hell of it, let me assume G is negative. No, sorry. Good place for a goat screaming. Steve said whenever we make a mistake, we can have a goat in the video screaming. So there's a good opportunity. We're replacing the potential with this thing. Okay, things become non-linear. It's going to be a bit weird, but that's fine. I can still think of this as an effective potential. Now, I mentioned earlier that this means that the system does not any longer obey the superposition principle, but my question now is to ask you to give me a physical meaning for this, this idea that there's a new bit to the potential that depends on the wave function itself. There's a new bit to the potential that depends on the wave function itself. What does that mean? Imagine that I obey the superposition principle and my fingers were sabres of light, or streams of light. Then my fingers could pass through one another. Superposition principle. This is a solution of the Maxwell equations for light, and so is this. Hence the superposition is. But now I do the experiment, right? And this happens. My fingers don't pass through each other. The system, me, whatever equations describe me, are not linear, because if they were, my fingers would pass through each other. There'd be a superposition principle. Does this help in asking the question, what is the meaning of this term?
The wave function's presence has an effect on potential.
Beautiful. The wave function's presence has an effect on the potential. The wave function interacts with itself. The wave function does not just interact with the potential, it also interacts with itself, just as I interact with myself. Yep. So the presence of the wave function affects the potential. Now, as an example, suppose that I just had a cloud of matter. This is just a cloud of gas in interstellar space. And let's just consider the example where there is no ordinary potential. There is no parabolic potential, for example. I would speak of this as a confining potential because it's in essence a bucket. But to get to the essence of what's going on here, let's pretend that this term didn't exist. And our Schrodinger equation, our Grosbetti-Esky equation looked like the following. That's a shorthand for d squared by dx squared. So we switch the potential off altogether. We just have this thing existing in free space. Now, never mind quantum mechanics. If I had a cloud of gas in interstellar space just sitting there, what would happen? Would it just stay as it is? Or would it evolve? It would expand. It would expand because? So it's a hot cloud of gas, it would expand because? Yeah, beautiful. So if this is a hot cloud of gas, then each of these particles would have a velocity in a random direction with a distribution of speeds, and this cloud would expand. So the fact that it has a non-zero temperature would lead to the cloud expanding. Let me now make t equal to 0. It's an important effect, but let's switch t equal to 0, or more precisely, let's assume that t can be assumed to be negligibly small. Now what would happen to the cloud? This is a cold cloud.
Stay together.
It would stay together. Could someone elaborate on this? Oh, gravity. So gravity would make it stay together. Can someone elaborate on this? will the cloud stay together and stay the same size? It'll get smaller. So the force of gravity would make this, this thing collapse. The one way of viewing this is that there's, it creates a potential well, going back to your point, that the wave function is interacting with itself. The wave function is contributing to the potential that pushes the wave function around. Here, the wave function creates a gravitational potential well into which it falls. So this is one way of viewing the gravitational collapse of a cold cloud. Again, it creates, the very presence of the dust creates a potential well into which it falls. This is just one way of looking at gravitational attraction. Similarly here, if you are at the centre of a given cloud, so this is now a cloud of wave function in 2D, there's no confining potential, but you have the wave function interacting with itself, and the potential here is going to be a maximum where the cloud is the densest, and it's going to be a minimum where the cloud is least dense, if G is positive. So if G is positive, will this term make the cloud expand or contract, and why? So if I drop the chalk, it moves from high potential to low potential. I'll ask the question again. If G is positive, the effective potential is going to be big here and small here. The wave function itself is creating its own potential with which it interacts. Will this term make the wave function expand, or will it make it contract? Expand, beautiful. That's correct, and it'll expand because?
It's like it's on a big hill and rolling down.
Beautiful, it's like it's on a big hill and rolling down. So this will drive expansion if G is greater than naught. This term will drive contraction if G is less than naught. By the way, they can do experiments where the sign of G is changed from positive to negative, in which case this term will drive expansion, then it'll drive contraction. This is given a whimsical name of a Bose-Nova. Work that one out, but it's like a bossa nova, as in a dance. It expands, it contracts, it expands, it contracts. Now this thing here, if we remember the spreading of the wave packet mentioning earlier, this term here tends to drive expansion. Yep. So there can be a balance here. If, for example, G is naught, then one of these terms is driving the thing to expand, one of the terms is driving it to contract. Which effect wins depends on how big G is. If G is negative enough, the contraction will win and the cloud will collapse. On the other hand, if little g is sufficiently small in magnitude, then even if G is negative and it drives contraction, this expansion will win. Ultimately, you have a complicated interplay between these two effects. And I want to take an aside and look at our diagram on the right. I've spoken about the interplay between theory and modelling. I love theoretical physics, I love computational physics, and I love experimental physics, and they're all interrelated. They're all very much interrelated. You have the theory, which is informed... Oh, sorry, let me ask the question. Can we talk a little bit about how these three prongs of physical science are related to one another, how they can complement one another? So if we were to look at a random link, let's say between theory and experiment, what do you see as the interplay between theory and experiment, in a very general sense of the term?
You start with theory to build an experiment to test it, or you can build a theory based on observations.
Beautiful. You can start with a theory and derive an experiment to test it, which could then be done. Or you could have an experiment. The surprising result of which informs you to develop a theory. Can I ask you to give someone who hasn't spoken yet an example of how a surprising result in an experiment can lead theory to evolve? And it doesn't have to be from within quantum physics. An example of a surprising experimental result that made us rethink physical theory. Beautiful. The null result of the Michelson-Morley experiment is one excellent example of how experiment drove us to rethink theory. I could have two more examples of how surprising experimental results made theory evolve.
Photoelectric effect.
Sorry?
Photoelectric.
Photoelectric effect, beautiful. One of the founding questions that disturbed physicists enough to develop quantum theory was the photoelectric effect. Again, experiment driving theory. And a third example, a third and final example.
Rutherford, most of the atom space was empty.
Yeah, beautiful. Rutherford scattering. Rutherford was expecting the scattered particles to bounce off the atoms as if they were big solid spheres touching each other. Instead, there was the insanely surprising result that atoms were mainly empty space, from which the nuclear model of the atom grew. How about the opposite, where theory, and this could be just pure mathematics or mathematical physics, where theory drives experiment? I'll give you one example, the photoelectric effect, right? Einstein predicts the photoelectric effect, and Millikan said, this is bullshit. I don't believe this is crap. I'm going to do an experiment to show why Einstein was wrong. Now, ironically, Millikan won a Nobel Prize for showing that Einstein was right, but this is an example of theory pissing off an experimentalist to do the experiment to disprove the theorist. And by the way, more often than not, the experiment disproves the theory, right? But in this particular case, it was Millikan versus Einstein. Both of them won, but this is one of many examples of where theory has provoked experiment to try and disprove the theory. Can we think of a more positive example of where a development in theory has driven experiment?
Even these nonlinear wave functions
Yeah.
that were hypothesized by Einstein in the 20s and
Yeah.
tested until the 90s.
Yep, absolutely. So these nonlinear wave functions hypothesized by Einstein in the 20s and not experimentally tested until the 90s. So let's have another link. How would modelling inform experiment? Suppose, for example, that I'm going to do an experiment next week on the Australian synchrotron, and I'm a company who's developing some new rubber for a tyre, and the Australian synchrotron is going to charge me $10,000 an hour to do X-ray experiments to determine which form of rubber has the best nanostructure. Now, I could just do 10 hours of experiments or 20 hours of experiments and see what happens. But the more modelling I can do, the better. If I can model or simulate experiments, I know my equations of physics, of how X-rays pass through rubber. I can model the different microstructures of the rubber, and I could model a series of experiments on my computer, which certainly does not cost me $10,000 an hour. I could then plan the experiment so that I can minimise the cost of the experiment by learning as much as I possibly can from computer modelling prior to doing a very, very expensive experiment. Can I have another example of how modelling could inform experiment? The idea of proposed experiments was mentioned earlier. It happens all the time that theorists write down equations that they can't solve. So they do computer modelling and they say, hey, here's an experiment that you could do. Never mind the fact that you need 10 times greater temporal resolution and 20 times smaller pixels and 100 times more efficiency than any detector that exists. This is a possible experiment that might be done in 5 or 10 years' time. So there are plenty of examples of modelling which predict experiments for which the technology doesn't yet exist. And so these experiments can be proposed and then they'll ultimately may or may not be done sometime later. Again, there's an interplay between modelling and experiment, between experiment and modelling. We've already spoken about the two different directions of theory informing modelling and conversely. Yep. You might also want to split, by the way, theory into physics theory and maths theory. As in pure maths, and these things also inform one another. So, for example, the pure mathematics theory of differential geometry certainly existed before Einstein applied it to general relativity. Now, I'm uncomfortable with having maths off to the side as if it's implying it's somehow less important. I see them as equally important, but these things also interplay. Let's say pure maths and mathematical physics. And these things can also interplay with one another. So, for example, Dirac and others such as Heaviside before him developed the concept of the Dirac delta, which then drove development in pure mathematics, where Schwarz and others made rigorous the theory of the Dirac delta and other functions which were similarly singular. This is a so-called theory of distributions driven by development in mathematical physics. The converse is also true. The pure math theory of differential geometry, developed by Riemann and others, drove developments in mathematical physics, for example, in the general theory of relativity. So there's many, many interplays here. As an example of this, let's take an apparent aside. And we spoke about a spin 1 wave function near the end of the last class. And we learned that if you have a spin 1 system, yep, you have some so-called axis of quantization. We learned that the spin 1 system can have 3 allowed projections, magnetic quantum numbers, -1, 0, and 1 respectively, and these vectors can in some sense be viewed as processing around the z-axis in this crude vector model of angular momentum. By the way, I've asked you a question about this in the second assignment, which has been uploaded to Moodle. So for the spin 1 system, we learned that the wave function that describes a spin 1 system actually has 3 components. A spin up component, an m equals 1 component, an m equals 0, and an m equals -1. And each of these is going to be a function of position and time. Now, just to make the notation slightly more compact, let me make these subscripts an up arrow, a sideways arrow, and a downwards arrow respectively. Again, these are all functions of position and time. Here's a question for you. I want to talk about the probability density, and I know that magnitude squareds of quantities gave me probability densities earlier, but we now have 3 wave functions which I can go ahead and magnitude square. Question, what is the physical meaning of each of these squared magnitudes? Are they probability densities? What are they? So let's take the first one. What's the physical meaning of this? Have a guess.
Probability you'll find it in the spin up.
Beautiful. It's a probability that you'll find it with a spin up. The probability of finding the spin projection to be m equals 1. More precisely, if you have some region of space with volume dx, dy, dz that I'll denote by dr at some time t, then this object will be the probability that you find the electron at time t equals 0 to be somewhere within this box. Similarly for this, with m equals 1, similarly for these two. How about normalization? Before, when we said that a wave function was normalized, I said that this is the probability of finding the electron within the box at a given time t. This is the probability of finding the electron anywhere. Hence, this is the normalization condition. Question, what does the normalization condition look like now? Again, I haven't told you this, but that's good because I want you to guess it. And I promise you, your guess is likely to be right. What is the normalization condition for a spin 1 wave function.
The same, but psi would be a sum of the 3 components.
Beautiful. Exactly the same, but we'll now need to add the 3 components. So what we're integrating over all space is the 3 probability densities, 1, 2, and 3. Now this can be written in a compact way, which is as follows. Instead of writing magnitude of squared psi squared dr, that could also be written as psi star psi equals 1. But when you have these multi-component wave functions, I invite you to prove this to yourself. If this is a dagger, then this normalization condition can be written more compactly as follows. We'll give these things a name, by the way. We call them, since these are spinors, these things are spinor wave functions. Now, an example of a spin 1 wave function, of a spin 1 spinor wave function, if you go to Lincoln Turner's laboratory, where he builds Bose-Einstein condensates. By the way, there's 2 Bose-Einstein condensate labs, but Lincoln's one has the word spinor, BEC. Yep. So what I want to do now is to ask the question about linking this idea of a spinor wave function with the idea of chaotic quantum mechanics. So we have a spinor wave function. And just to keep life, to minimise chalk, let me deal with a 2-component spinor, right? So if we were to have a 2-component spinor, which is a spin-half system, spin half, the allowed projections would be plus or minus a half. Then our spinor wave function would have an up component and a down, both as functions of position and time. So what I want to ask is, what equation governs the evolution in space and time of this spinor wave function? Now, let me begin to answer the question and then throw out to you. I say, look, I don't know, but I do know the Schrodinger equation. So let me write down the Schrodinger equation. So there's the Schrodinger equation. There you go. That's what I do know. This is the Schrodinger equation for one wave function. Now, I'm not going to ask you what the equation is. I want to ask the more general question. What would be possible equations for governing the evolution in space and time of this pair of wave functions? What would be the simplest possible answer to this question? So imagine you know quantum mechanics. Empty your brains of everything you know about quantum. Then I tell you that a wave function obeys a certain equation called the Schrodinger equation. I now have two wave functions. What would be the simplest answer to the question of what equation would that pair of wave functions obey? A pair of Schrodinger equations. Excellent. So let's write down a pair of Schrodinger equations. So I've written down the same Schrodinger equation twice, and I'm going to have one Schrodinger equation for the spin up and one for the spin down. Will these potentials necessarily be the same? No. And what would be a reason why the potentials would not necessarily be the same?
Like before you said, where it's dependent on the wave function.
Yeah. So these potentials could depend on the wave functions themselves. Another reason that the potentials might be different is that these things have spin. If, for example, I have a magnetic field floating around, then spin up and spin down will have different energies and therefore different potentials. So this potential could depend on both the spin and on the wave function itself. Now let me ignore the complication of spin. You've made a statement that the potential could depend on the wave function itself. So let me just indicate that as V as a function of psi1 and V is a function of psi2. So I'm ignoring the fact that spin could have different V's, and it may well, and in fact does in general. But let's consider the wave function interacting with itself. So I've got V as a function of psi1 and V as a function of psi2. Now I look at that and I'm unsatisfied, and the reason I'm unsatisfied is because these things are completely independent of one another. Here we just have two wave functions, two clouds, the psi up cloud and the psi down cloud, each obeying independent equations, and these equations are not coupled to each other. In other words, the existence of one wave function does not influence the other, and conversely. How could I fix this? There's no one answer to this, but I'm looking for a simple answer. How could I fix this? So my equations are not coupled. My first equation only has psi1 in it. My second equation only has psi2 in it. I want these two wave functions to talk to each other. I want them to interact. I want them to couple. How could I do that?
Both potentials got to be in terms of both wave functions.
Yep, beautiful. I need to have both potentials in terms of both wave functions. Now, in general, these potentials will be different. So let me actually put an up and a down subscript here. Not necessarily, but they in general will be different. What you've just discovered is the gross Paganin equation for spin bosons on condensates. Now, determining the particular form of this is going to be beyond the scope of today's discussions. But the point is, there's a whole raft of theories, and depending on which approximations you make, you'll get different results. But all of them have the character of a special case of these equations. Because of these terms that depend on the wave function, these things are intrinsically nonlinear. But now we have a pair of fields, psi up and psi down, which interact with one another via a nonlinear generalization of the Schrodinger equation. These equations also typically can't be solved exactly, and one can study spinor BECs by numerically solving these. Analysis can go quite a far way, though. Having said that, this is one of the hottest topics, by the way, in modern physics. I'll stop there, and I'll see you for a pair of lectures on Friday.